Hello everyone, welcome to my presentation. My name is Guocong. I'm from the Ohio State University, and today I will present one of our recent work. In this work, we investigated the optimal offline prefetching and caching with the objective to minimize the service costs. First, let's look at some background. Nowadays, caching are used everywhere to store the data closer to users. For example, if you have a user at the edge of the network and need some data, we will first check whether the data is stored in the cache. If it is stored in the cache, which is a cache hit, then we can serve the user immediately with a low latency. However, if the data is not stored in the cache, which is called a miss, then we have to get the data from the backend data storage and serve the user. This process may incur a large delay, and we would like to have as few misses as possible. One approach is to use prefetching. Imagine that now we can predict the user demand in the future, and we know that the future requests might not be stored in the cache. Then we can prefetch the data from the backend storage and store it to the cache before the user actually requests it. And when the request arrives, the user can get data from the cache directly with a low delay. The prefetching and caching have a lot of benefits. For example, the service delay is very low. Furthermore, prefetching is less time sensitive compared to fetching, because when you prefetch the data, the requests have not arrived yet. Then we are wondering whether prefetching is always a good option. If it is not, when should we prefetch? Before answering these two questions, let's first look at the problem formulation. In this paper, we consider a set of data items, which is denoted by DI, and we use Rn to denote the requests for those data items. And we assume that the request of sequence is known, which means we focus on the offline cases. And there are two data retrieval options. The first one is fetching, and the second one is prefetching. Fetching should be done after the request arrives, but prefetching is done before the request arrives. Because of these differences, we should have different caching options. For fetching, we can directly use the data from the backend storage and serve the user. We do not need to store the data in the cache. However, for prefetch, since the requests will arrive in the future, we have to load the prefetched data in the cache and store it until the requests arrive. And in this problem, we consider a cost-based model, which means we assign different costs to fetch and prefetch. The fetching cost is set to 1. For prefetching cost, considering the benefits of prefetching, we set it to be a constant C, which is between 0 and 1. Then we formulate the optimal offline prefetching and caching problem. The objective is to minimize the overall cost by choosing proper data retrieval options. And the constraint is that the cache size is limited, which means we cannot store every data in the cache. To solve this problem, it is equivalent to answer the following two questions. Question 1, should we prefetch or fetch a requested data item if it is not stored in the cache? And second question is that if we need to load a new data into the cache, which item should be evicted? And in this paper, we propose a flow-based optimal offline policy to solve this problem. Specifically, for each request sequence, we will first construct a flow network. And for example, if we have a cache of size 2 and the following request sequence, we will construct such a flow network where each request is represented by a bunch of nodes, and the nodes are connected by edges. In the paper, we will give detailed information about how to construct such flow networks. Once we have a flow network, we can use existing algorithms to find the minimum cost flow, and the expected time for those algorithms is O(n) to the power of 1.5. Here n is the length of the request sequence. Then, using the minimum cost flow, we can reconstruct the optimal prefetching and caching policy. And this is the basic idea of the flow-based optimal offline policy. You might notice that this flow-based optimal offline policy has some drawbacks. First of all, it cannot analytically answer the two proposed questions. Second, you need to know all future requests to construct the flow network and to make optimal decisions. Furthermore, the decision of a request is unavailable unless the entire sequence is processed. To overcome the drawbacks, we will analytically characterize the properties of the optimal policy, and then using these properties, we will design an effective and efficient approximation policy. First, let's recall the two questions. Question 1, should we prefetch or fetch? And question 2, which item should be evicted? And it turns out that the second question is easier to answer. We prove that there exists an optimal policy that always evicts the farthest in future item. The farthest in future item is defined as the item that is stored in the cache and requested farthest in future. Once we have this eviction policy, we are ready to answer question 1. Assuming the first in future eviction policy is adopted, we prove that prefetching is the optimal choice if any of the following conditions is satisfied. Condition C1 says that there exists a request for a popular item in the near future, but that item is not stored in the cache. And C2 says that the prefetching cost is low enough. And in the paper, we will give concrete mathematical descriptions for the popular item, the near future, and the concept of sufficiently low. But here, we need to notice that in order to check whether these two conditions are satisfied, we only need near future information. This is very helpful for us to design efficient and effective approximation policies. And here is the approximation policy pi A. Pi A will choose to prefetch an item if the prefetching cost C is less than a constant or any of C1 or C2 is satisfied. We claim that pi A only requires near future information because we will only need limited information to check whether C1 or C2 is satisfied. Moreover, the time complexity of pi A is O(n), which is better than the complexity of the offline optimal policy. And we will show that pi A can achieve near optimal performance. First, we analyze the worst case performance by deriving the competitive ratio. Here we introduce two benchmark policies. The always prefetching policy pi P will always prefetch the item if it is not stored in the cache. And the always fetching policy pi F will always fetch an item if it is a miss. In the paper, we derived the competitive ratios for those policies as functions of the prefetching cost C. And here we plot the result in this figure. And the black curve is the competitive ratio for the approximation policy pi A. We can observe that the competitive ratio of pi A is 1 if the prefetching cost C is less than 0.5 or equal to 1, which means for those C values, our approximation policy can achieve the optimal performance. And second, the competitive ratio of pi A is at most square root of 2. Furthermore, we can also observe that pi A always achieves the smallest competitive ratio among these three policies. This competitive ratio analysis shows that for the worst case, our approximation policy can achieve reasonably good performance. And next, we will show its average performance using simulations. In the evaluation part, we will introduce another benchmark policy, that is the optimal static policy pi s. Here we assume that pi s only knows the popularities of each item and has no information about the request sequence. So it will store the most popular items in the cache and will never update the cache content. We consider a cache of size 20 and use pi to denote the popularity distributions. First, we conduct the simulation for exponential popularities, and we plot the cost per request as a function of C. Here, the orange curve is for the optimal policy and the black curve is for the approximation policy. We can observe that pi A achieves near optimal performance. Here, the red curve is for the always prefetching policy pi p, and you can see that when the prefetching cost is small, pi p achieves very good performance. But when the prefetching cost C is relatively high, for example, around 1, then the performance of pi p is much worse, and is even close to the performance of pi s, which has no information about the request sequence. Next, we repeat the simulation for different popularity distributions with different tails. When the tail of the popularity distribution becomes heavier, the differences between pi p, pi a, and the optimal policy is getting smaller and smaller. The reason is that when the popularity has a very heavy tail, the requests are less concentrated. As a result, the condition C1 and C2 are more likely to satisfy it, which makes prefetching almost always the optimal choice. In the second experiment, we will show that our approximation policy pi a will only need near future information. Here, we use T to denote the number of future requests that is required by pi a to make decisions. And we consider a Zipf's popularity distribution. We show the statistics of T using these box plots. Here, the green plots represent the mean, and the red bar in the middle is a median, and the blue box represents the 75 and 25 percentiles. In the first figure, we can see that T will not scale with a trace length, which verifies that we will only need limited information to make decisions. A similar phenomenon can be observed in the second figure. But in the third figure, we can see that T will increase with the cache size. In practice, if the cache size is fixed, but the requests keep arriving, our approximation policy will only need a limited amount of information to make decisions, because T will not scale with a trace length. Now let's make a summary. In this paper, we formulated a cost-based optimal offline prefetching and caching problem, and we proposed a flow-based policy to solve this problem. Furthermore, we analytically characterize the properties of the optimal policy. Specifically, we show that the first-in-future eviction is optimal. We also provided sufficient conditions for optimal prefetching. By using those insights, we designed a lightweight approximation policy, and this policy only requires near-future information, but achieves near-optimal performance. This is the end of my presentation, and thank you all for your attention. Any questions are welcome.